In this video, we'll be talking about inverse functions. We'll learn how to find the outputs of inverse functions, and we'll also learn how to identify when a function has an inverse or not. To begin, an inverse function is a function that reverses the operations of another function. Let me draw a picture of what we mean by this. Let's say we have a function named f. An inverse function is something that we'll label as f with a little -1 as the superscript. We call this f inverse. Now here's what we want this inverse function to do. Well, whenever we plug in any input into the f function, the f function will perform some operations on that input and give us some output, which we'll label y. Now the inverse function is supposed to undo those operations. So if we take y and we plug it into the inverse function will undo all of those operations and give us back what we started. It should give us back the original input x. The diagram that we've drawn here gives us a way to describe a function and its inverse. When we take an input and we plug it into one function and take the output and plug it into another function, what we're doing is a composition. And the relationship that we have here is that when we do the composition, f inverse composed with f, we see that when we input x, the output is also x. So in general, for any function f, its inverse function, which we call f inverse, is a function such that when we do the composition, f inverse composed with f, when we input x, the output is also x. Let's take a look at an example of a function and its inverse. In our example here, we're given the table of values for f, and we want to fill out the table of values for its inverse function, f inverse. So here, for f, we have the following table. Let's take a look at some of the entries in our table and see what those entries can tell us about the inverse function. For example, our first entry says that when we input 1 into the f function, we get 3 as the output. Let's draw that in our diagram. When we input 1 into the f function, the output is 3. So according to our diagram, if we input 3 into the inverse function should undo the operations of f and give us back the original number that we started with, which is 1. So looking at this right-hand side here, we see that when we plug in 3 into the inverse function, we get the output 1. So for our table for f inverse, when we input 3, the result should be 1. Let's look at another entry in our table. Here, when we input 2 into the f function, we get the output 5. So in our diagram, if we input 2 into the f function, we get the output 5. So according to our diagram, if we take 5 and we plug it into the inverse function will undo the operations that f did, and it'll give us back the original number that we started with, which is 2. So we see that when we plug in 5 into the inverse function, we get the output 2. So in our table, when we input 5, we should get the output 2. Let's look at our next entry. Here, when we input 3 into the f function, we get 4. So in our diagram, when we plug in 3 into the f function, we get the output 4. So if we take 4 and we plug it into the inverse function will undo those operations and give us back the number that we started with, which is 3. So looking at this right-hand side here, we see that when we input 4 into the inverse function, we get the output 3. So in our table of values, when the input is 4, we see that the output here should be 3. Let's look back at some of the entries that we have here and think about them as points on a graph. Our first entry here tells me that the point 1, 3 is on the graph of the function f. Now on my inverse function, we have this entry, which corresponds to a point 3, 1. So 3, 1 is a point on the graph of my inverse function. Next, if we look at this entry on my table for f, we see that we have a point 2, 5 on the graph of f. Now for my inverse function, we have this entry, which corresponds to the point 5, 2, which will be a point on the graph of F inverse. And then if we look at this entry, we have 3, 4 on the graph of F, but then on the graph of F inverse, we have this entry, which corresponds with the point 4, 3. What we observe is that the coordinates of the points that we have on F are flipped for F inverse. So if we have the point x, y on the graph of F, then y, x would be a point on the graph of F inverse. This also tells us that the inputs and outputs are flipped when we compare F and F inverse. So let's use this idea to help us finish filling out our table. In our table for F, we have this entry, which corresponds to the point 4, 2, which means that for our inverse function, we should have the point 2, 4, which means when we input 2 into the inverse function, we should get 4 as the output. Our last entry here for our table for F is 5, 1, which means that for my inverse function, I should have the point 1, 5. So when we input 1 into the inverse function, we should get the output 5. Let's take a look at some more examples. In our example here, we're given another table for F. This time when we input 1, 2, 3, 4, 5, we get the outputs 5, 3, 1, 2, and 4. So let's figure out the corresponding table of values for the inverse function, and let's try to fill this table out from left to right. The thing to remember is that when we compare F with its inverse function, the inputs and outputs are flipped. So if we want to figure out the output of the inverse function when we input 1, we want to look at the F table and see where 1 shows up as the output. In my table for F, 1 shows up as the output here. When we input 3, we got the output 1. So for my inverse function, when we input 1, we should get the output 3. For the next entry in our F inverse table, we want to figure out what's the output to the inverse function when we input 2. So we want to go to our F table and look at where 2 shows up as the output. In our F table, 2 shows up as the output here. In this entry, when we input 4, we get the output 2. So for my F inverse, when we input 2, we should get the output 4. For F inverse of 3, we want to go to our table for F and see where 3 shows up as the output. We have this entry here. When we input 2 to the F function, we get the output 3. So for our inverse function, if we input 3, we should get the output 2. For F inverse of 4, we look at where 4 shows up as the output for F. We have this entry here. When we input 5, we get 4 as the output for F. So for my F inverse, when we input 4, we should get the output 5. And then lastly, for F inverse of 5, we see that 5 shows up as the output here. When we input 1 into F, we get the output 5. So for our inverse function, when we input 5, we should get the output 1. Let's take a look at one more example. In example C here, we're given the function f with the following table. When we input 1, 2, 3, 4, and 5, we get the outputs 3, 1, 5, 3, and 2. So let's try to fill out the table for its inverse function. For f inverse of 1, we want to look at our table for f and see where 1 shows up as the output. We have this entry here. When we input 2 into the f function, we get the output 1. So for our inverse function, when we input 1, we should get the output 2. For f inverse of 2, we want to look for 2 as the output to the f function. We have this entry here. When we input 5 into the f function, we get the output 2. So for the inverse function, when we input 2, we should get the output 5. Next, for f inverse of 3, we want to look at where 3 shows up as the output in my f function. The issue here is that 3 shows up in two places. We have this entry, 1, 3, and also this entry, 4, 3. So for f inverse of 3, is the answer 1 or is it 4? Let's remind ourselves what f inverse is supposed to do with our diagram. For any input that we plug into the f function, if we take the output and plug it into the inverse function, we should get back the original number that we started with. So in our example here, let's look at this entry. If we input 1 into the f function, the output is 3, which means when we input 3 into the inverse function is supposed to undo all of the operations of f and give me back the original number that we started with, which is 1. But now we also have this entry, 4, 3, which means that when we input 4 into our f function, we're also getting 3 as the output. But plugging 3 into the inverse function, we already have the output 1. But that's not what we want from our inverse function. We want the inverse there to give us 4 because that's what we plugged in originally. Now, for a function, one input can't give more than one output. So it's impossible for f inverse of 3 to be both 1 and 4. For that reason, we say that this function f does not have an inverse function. So in general, we see that not all functions have inverses. In our example here, we see that there's a problem when two different inputs to the f function gave us the same output. When we have something like this, it's impossible to come up with an inverse function that does what we want. So from our previous example, we learned that a function has an inverse if and only if all of its outputs are distinct, meaning every input is giving you a different output. Functions with all distinct outputs are called one-to-one functions because each input is giving you a unique output. You never have two different inputs going to the same output. So it turns out we can tell when a function is one-to-one by looking at its graph. We can perform something called the horizontal line test. The horizontal line test is very similar to the vertical line test. We can tell if a function is one-to-one if every horizontal line crosses the graph of the function at most once. Let's take a look at some examples. In our example here, we want to determine if the following functions have inverses. So what we'll do is use the horizontal line test to determine whether or not they're one-to-one, and if they are one-to-one, that tells me they have inverses. So let's start with example A. Here we have the function f of x equals x cubed. To perform the horizontal line test, we just want to draw horizontal lines through our graph and see how many times these horizontal lines cross our graph. We see here that each of these horizontal lines just crosses our graph at one point. This tells me that our function passes the horizontal line test, which means that our function is one-to-one. And if it's one-to-one, that means our function has an inverse. Let's now move on to our next example. In example B, we have the function g of x equals x squared. And once again, we'll perform the horizontal line test by drawing horizontal lines through our graph. We see here that each of these horizontal lines cross our graph more than once. For example, let's look at this middle horizontal line. It has two crossings. Let's label the x values where these crossings occur. We'll call this x1 and we'll call this x2. Since the points at x1 and at x2 are on the same horizontal line, we know that they have the same y value, which means that when we input x1 into our function and when we input x2 into our function, we're getting the same output. So for our function g here, since there's a horizontal line with more than one crossing, we would say that it fails the horizontal line test. And this tells us that our function g here is not one-to-one. There are two different inputs that give me the same output. And since g is not one-to-one, it does not have an inverse function. Let's now take a look at our last example. Our function h of x is the 1 over x function, and here let's perform the horizontal line test by drawing horizontal lines through our graph. We see here that our horizontal lines each cross our graph once. This tells us that our function h here passes the horizontal line test, which means h is a one-to-one function. And since it's one-to-one, we know that it has an inverse. So in this video, we learned about inverse functions. We learned how to fill out a table of values for them, and we also learned how to use the horizontal line test to decide whether a function has an inverse or not.